Hi, and welcome to my AP Physics lesson on circular motion, specifically the circular motion that involves a car going around a banked turn of some kind. So as you can see, I have my awesome vehicle here going around a banked turn. So it is coming at us, and there is an acceleration of some kind. That acceleration is actually acting towards the center of the circle. So of course, viewing it from above, that is not a circle. So viewing it from above, we would have that vehicle. Here, let's draw this vehicle. So there's the vehicle, and at that moment in time, it is in fact accelerating this way. So that's its acceleration, while its velocity is this way. So velocity versus acceleration. And so what's happening here, and in fact, maybe let me put it a little bit closer to the center of the circle. So what's happening here is that the object is moving. This is its tangential velocity along its circular path. There is a bank to this turn. Without a bank, of course, friction would be the only force acting on it towards the center of the circle. However, what we actually would like to do is figure out given some velocity, what would the bank of the turn need to be? What angle would it need to be in order for there to be no friction necessary? So what would this angle theta be in that case? So let's take a look at that and see if we can figure out what the angle would have to be in order for there to be no friction. So if I were to sort of redraw this a little bit, I'm going to do it fairly small, I think. So I'm going to redraw this banked turn just that way I can make a free body diagram. So here's my block, which is the vehicle. We have a few forces acting where we have mg acting down, and then we have the normal force acting off in this direction. And you should recognize that those are the only two forces acting on it. If there was friction, then friction would be probably acting maybe this way or acting this way. So it kind of depends on whether you want to go, sort of up or down the inclined plane. But in all reality, well, that's not what I wanted to do. In all reality, in all likelihood, you would have friction that would be moving in this direction down the inclined plane because you're trying to help the vehicle go around this banked turn. In all likelihood, you're probably going faster than what's necessary, but that's not necessarily true. If you're going really slow, then maybe you would need friction up the plane. So, but we'll tackle that another time. So let's start off with trying to figure out what angle would be necessary. So what we'll do is we will basically look at this in terms of its x and y coordinates. Now, when you look at an inclined plane problem, so let me draw that here real quickly. So an inclined plane problem, just a basic inclined plane problem, where what we would do is we would say, okay, this is the x component, the x-axis, and this is the y-axis, and we kind of tilt our head when we look at that problem, because the object is going to accelerate down the plane, and that's why we do that, because we want to make the x direction the same as our direction of acceleration. However, in this case, we are not doing that. We are going to keep our head straight and level, and this will be the x direction, that will be the y direction. Why? Because it is accelerating to our right in this view. And so we want to keep the acceleration in the direction of one of the axes. So with that in mind, let's look at the sum of all forces. In fact, let me write just a little bit bigger. Okay, so we want to have the sum of all forces acting in the y direction, and that of course is going to be equal to ma, and in this case that ma is in fact equal to 0 because it's not accelerating up or down. Okay, so it's not going up the inclined plane nor down the inclined plane. And so what else can we say about that? So we can say that is, okay, so we have mg acting down, so I'm going to say that's a negative mg. And then what forces do we have acting up? Well, let me break this down, or let me break the normal force down into its x and y components. Okay? And so what you should recognize that if this is angle theta here, then this should also be angle theta here as well. So that means that the y component of the normal force is going to be this side of the triangle. So what I'm going to start off by saying is that that the sum of forces in the y direction, we have the negative force of gravity acting down, and we have in the opposite direction a positive direction we have the normal force, but we have the y component of the normal force. So what is that y component? So let me just kind of start from here, where 0 is equal to negative mg, and we should recognize that the normal force in the y direction is the cosine. So this is going to be plus the cosine of the angle theta times the normal force. Okay, and so that means that the normal force is equal to, and that's what I'm going to do, I'm going to solve for the normal force, and I'll explain why in a moment. And so that means that the normal force is equal to, let's see, we have add each side by mg and divide by cosine theta. Okay, so that is the normal force, and I'll come back to that in a bit. So, in fact, let me explain for a moment why I'm solving for the normal force. So basically what it comes down to is that I have two unknowns. The mass is fairly irrelevant. The gravity I want to keep in this, it's irrelevant, but you'll see why later. In fact, it's not even necessarily irrelevant, it's just not something I can change. So I'm essentially looking at it to where I have two unknowns. I have the normal force, which is one of the variables that I don't care about because it's completely dependent on the mass. It's completely dependent on the velocity. And so I have the normal force and I have the cosine theta. It bothers me not to have parentheses around that, so I'll do that. And so what I want to do is, since I have two unknowns, I want to make two equations, one for the y direction, one for the x direction, and then I'm going to set both equations to one of those unknowns, and then I'll be able to solve for the other. So I'm solving both equations for, or setting them equal to the normal force, and then we'll set those two equations equal to each other. So let's go ahead and look at the sum of all forces in the x direction, which is equal to, okay, so let's see what's going on in the x direction. So in the x direction, this is, let's see, we have the normal force in the x direction, right? So that is the force that is acting off and to the right, and that is actually the only force that is really acting on it in the x direction. So I'm going to say that this is equal to, and let's take a look, that's the opposite side of the triangle, so this is equal to the sine of angle theta times the normal force. Okay, but what else can I say? I can say that this is a centripetal force, right? The sum of all forces in the x direction, that is the direction of its acceleration. So I can say that this is a centripetal force. Well, what is a centripetal force equal to? That is equal to m times v squared over r, which is just our equation for circular motion forces, where the acceleration is v squared over r. That is its tangential velocity, right? That's this here. That's the tangential velocity over the radius. And so, well, v squared over r. And so we are going to use those components. We're going to use this part, right? This stuff off to the right. So I don't need this little f sub c anymore. That was just there to kind of like come to this realization. So let me maneuver all this around to solve for the normal force. So this means that the normal force is equal to, okay, so we basically just divide each side by sine theta. So that means that we have m times v squared over r, and it's specifically sine theta r. That's a theta. Try and improve that. Okay, so that is the normal force. And so what I'm going to do is I'm going to set those two equal to each other. Okay, let me actually move this up just a little bit so I have some more room. And let me go ahead and rewrite that. So I have mg over cosine theta. Okay, right, so I just rewrote that, and that is equal to this stuff here. So that's m, I said m, but wrote v. Oh boy. So that is m v squared over sine theta r. Okay, and so what we want to do is we want to solve for theta. So let's go ahead and get all the thetas off to one side, and then we can isolate the theta by itself. So what do you say? Let's take a moment to look at this. What we can do is we can multiply each side by sine theta and divide each side by mg. So let's go ahead and do that. So that means that it's going to be sine theta over cosine theta, and that's going to equal mv squared over, let's see, we have to divide each side by mg, so that's over mg, right? The m's cancel, and I think I'm leaving out the r. The r is still there, right? The r is still there, so that's, yep, okay. So divide each side by mg, the mg goes here, multiply each side by sine theta. Okay, it looks good. The m's cancel, and so that means that sine theta over cosine theta is equal to v squared over gr. Of course, the sine theta over cosine theta is equal to tangent theta, and so my last step is to actually get the theta alone. So that means that, and I'll just write that over here so I have some space so my head's not in the way. That means that the inverse tangent of all this stuff, the v squared over gr, v squared over gr, or otherwise known as grr, equals theta. Sorry, I can't help myself. And so that is how you solve for the angle theta, given that you're moving at some velocity around, along the tangent around a banked turn. So that means that if you're moving at just the right velocity, no friction would be necessary, and you can just go around the turn without sliding up or down. If you've ever seen, maybe in like an old mall, because who goes into malls anymore, but there's those sort of toy machines where you put a coin into it and you see the coin kind of like going around this conical sort of thing. And so given that it's moving at some velocity, the coin is going to be able to stay on that part of the track. But since the coin is always losing velocity, it must go along a smaller radius, right? So that should actually make really good sense. So as this shrinks, this needs to shrink as well, because the conical shape of that thing stays the same. So the angle stays the same. So in order for the angle to stay the same, velocity decreases, radius must decrease as well, hence it goes into a smaller radius as time goes on. Okay, so I'll have another video that goes over how to solve this problem with forces that are along the plane. So those forces would be in that direction, typically speaking. And we basically will just kind of add that to it. So we'll break the friction force into its x and y components, right? And notice that the y component would be going actually in a negative direction along with gravity. And you would just literally add those right in with these equations. So I think I'll make that into a separate video, so that way this one doesn't run too long. And I hope this was helpful. You guys let me know, and you guys have a great one. Take care.